All right, so hi everyone. I guess we are live now. So welcome back. Myself, Ayush Tripathi, mentor and the problem setter at Geeks for Geeks, and welcome you all to this post analysis session of last Job-A-Thon 40. So kindly just please confirm if I am audible in the chat box, and also tell me how was the contest and rate the entire contest on a scale of 10 to 1. All right, so yeah, just rate this entire contest on a scale of 10. And I personally categorize this problem, this entire all the problems from easy to a medium level, especially the first two problems. The first two problems were very easy. The last problem uses a very advanced data structure, which is binary lifting. And using binary lifting, you can find the LCA in just logarithmic time. So this gonna be the prerequisite for the last problem. And for the first two problem, there is no prerequisite at all. So let me check if everything is fine. Cool. So let me just quickly share my screen and then we'll simply start with the first problem and then second and finally the last problem. So I hope my screen is visible to you all. So yeah, this was the first problem. Minimize the purchase. So you can see your scores on our dashboard. So minimize the purchase. So in this problem, you are planning to purchase n items and where the cost of the ith item is price of I. The price array which will be given to you. Price of I rupees. And you also have a K coupons and each offering a discount of X rupees that can be applied to any item. So basically you have K coupon and each coupon will reduce the price of item by X. And here how the coupons work. So you can use any number of coupons including none on each item. That is on a single item you can use multiple coupon. And if you use M coupons on an item with the original price of a price of I, then the price will reduce and becomes maximum of 0 comma 0 comma price of I minus M into X. A very straightforward thing. The price has reduced by M into X. Each coupon will reduce the price by X and I have used M coupons here out of the K coupon. And we need to determine the minimum total cost of buying all the items by distributing the coupons in the most effective way. And here another thing, the test cases are generated in such a way that the answer is always fit in a 32-bit int. So you don't need to worry about the overflow case. And you don't have to use the long. Integer data type will work for all the test cases. So yeah, now let's just quickly discuss the solution. So we have K coupons. initially, and we have a price array. So let's call this as P, and this price array would be of size n, and you need to purchase all the n items. So it has some integers. So let me just quickly check. So if I apply m coupon, if I have applied m coupon on some item with the price of pi, then what will be the new effective cost? So this is simply equals to, this will just simply reduce to maximum of 0 comma p of I, and minus m into x. For every coupon the cost will reduce by x, and I have used m such coupon, and we need to find the total minimum cost that we need to pay to purchase all the n items using these k given coupons effectively. So the very first observation, I do not want this value to be turned out negative, because then it does not make any sense. Then you are not using the x completely if this value has turned out negative. So what I'm trying to say, we want either this to be turned out to be 0 or something greater than 0, because I want to use every single coupon completely. That is, for every coupon I want to reduce its price by x. But there might be the case when, let's say, the value of x, well, let's say the value of x is 5, and p of I is equals to, let's say, 3, and then let's say we have another integer p of I plus 1, the next item, and its price is equals to 5. So if you use the coupon at here, if you use the coupon at here, then it will not give you the best result. The best result is to use the coupon at here. Cool. So what I'm trying to say, I want to utilize this value of x completely, because here if you subtract 3 minus 5, then this is simply a negative number. So p of I minus m into x, this must be equals to 0 or something which is greater than 0. So what will be the value of m? Here I know the value of x, I know which is constant. The value of p is also constant. So how I can find the value of m? So m is simply equals to p of I divided by x. P of I divided by x. And I will take its floor value, because there might be the case when you are left with some remainder. So do not waste the operation. Do not waste the coupon. Use the coupon and keep the remainder as it is, and use the coupon for some next item, for some another item. Because if you use the coupon for the remainder, then you are not using the value of x completely. So yeah, this is the idea. This is the idea to solve this problem. And there might be the case when at the end, I am left with some items and some coupon. So what will happen in that case? So let me give you some example. So let's say the price that we have is a 6, and the cost of a first item, then let's say we have a 5, and let's say then we have a 8, or let's say 9, and here let's say the value of k, the value of k is 5, and the value of x is 4. So here in this case, how many time I will use the coupon here? So for the first item I will use the coupon only one time, so its price will reduce by 4, sorry. So it price will reduce by 4. Then for the second item, again I will use the coupon for one time. Then for the third item, I will use coupon 3 time, not 3 time but a 2 time. So its price will reduce by 8. 4 into 2, 2 coupons. Cool. And now I am left with the one coupon. So 5 minus 4, 4 coupon I have used. one coupon for the first item, one coupon for the second item, and two coupons for the third item. So now I am left with this one coupon. And what will be the new price of the item? So it is 2, and this is 1, and then this is also 1. So where I will use this remaining one coupon? So I will use this remaining one coupon here. So this simply means after 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 iterating over all this entire array, and if you are left with some coupon, then from here we know that these new values are always less than x, because these are remainder, right? These are the remainder. So these values are always lesser than x. So which remainder I will select? I will select the remainder which has the maximum value, that is k, that is a one largest element from here. Whatever the remaining coupon you have, let's say it is k dash. K dash is the remaining coupon, and so from here I will just simply select k dash largest element. And this is the complete solution. So is the approach is clear to everyone? Let me just change this layout. You can check your score from the scoreboard of the contest. So is the approach is clear to you? Just write a quick +1 so that we can quickly discuss the implementation and we'll move to the next problem. So yeah, here is the implementation. This is the method that you need to complete. Minimize the purchase. So here the total cost that I have initialized with 0. This is my answer. Then I will iterate over all the items, and this is the maximum value of m. This count is the maximum number of time that you can perform the operation on the current item. So this is simply equals to floor value of item price and divided by x. Cool. And after this we are left with some remainder. So then how many time I can use this coupon here? So this is simply equals to minimum of k comma count, because there might be the case when the value of k is less than this count. You required count a number of coupon, but you just only have a k number of coupon. So in that case we need to select the minimum. So now the value of k is simply reduced by used coupon for this current item, and the item price will simply reduce by m into x. That is number of time I have applied the coupon here and multiplied by x. And then I will sort this array. And if I am left with some coupons, so then I will select. I will pick the k dash item with the largest remaining price and apply the coupon over those items. And I need to only pay for the remaining n minus k items. Here k is the remaining coupons that you have, and this is the total number of items. So I will I just only need to pay for n minus k items. And there might be the case when the value of k is greater than n. So in that case, this value turns out to be negative, and that's why here I'm taking the maximum with 0. Because there might be the case when you can purchase all the items for free and you are still left with some coupon. So this is the case where I will handle this negative wala case. Cool. And now just simply iterate from 0 to n minus k, and you need to pay for these items only. And what will be the time complexity? So the time complexity is n log of n base 2, because now you are sorting this array of size n, and the space complexity is constant since I have not used any extra space such as array, string, or something. So this is the complete implementation. So I hope this is clear to everyone. Now let's just move to the next problem. Yeah, this one. Solve the expression. So how many of you were able to solve this problem? You just only need to draw some casework, and that's it. And it uses a very standard technique. Okay, so if you haven't solved this problem, then make sure to remember the approach that we are going to discuss. So solve the expression. In this problem, you are given two arrays, A and B, each of length n, and your task is to select some subset of indices. Let's call this as A S, and it is simply a subset from the set 1 to n. That is, you need to select some subset of indices, and here one base indexing has been considered, such that the size of S is exactly equals to k. So you need to pick k indices, and for every chosen subset, calculate the value of PS. The value of PS is defined in this way: the maximum element, the largest number from array A, present among the selected indices. All the indices that you have picked, you need to select the maximum value of A of I among those picked indices, and then you need to sum all the numbers from array B which are present at the selected indices. And now the value of PS is simply equals to the multiplication of step 1 and step 2 values. So this can be simply represented in this way in mathematical terms. And here this I belongs to S, the set of indices that you have selected. And we need to determine the minimum possible value of S. So for this problem, any greedy solution won't work here. So now we need to consider every possible case. Cool. So let me just give you some example here. So 376 and then 924. And array B 9, 2 and 4. And the value of k is equals to 2. This simply means you have to pick two indices. So let me write it this way, capital A and capital B. So here what I can do, I can pick these two indices, that is index 2 and index 3. So in this case, what will be the value of PS, that is my answer, is simply equals to maximum element of array A among the pick indices. So the maximum element here in this case is 7, and then sum of all the elements which are present at the pick indices of array B. So 2 plus 4. So 2 plus 4, which is equals to 6. So this is simply equals to 42. And this is the minimum answer that you can achieve. So there is a technique which is called as contribution technique. So here, one thing that I know, I cannot iterate over all, I cannot find all the subset of size k, and then for every subset, I calculate the value of PS. This is not possible because the constraints are up to 10 power 5. The value of n can be up to 10 power 5, and the value of k can also be up to 10 power 5. So these constraints do not allow you to write the recursive solution to find all the subset of size k. We need to do something better. And yeah, this is not a completely greedy solution, but a very close to the greedy solution. So there is a technique which is called as contribution technique. Contribution technique simply says that if you want to be able to iterate over all the sample spaces, iterate over all the possibilities, then you need to find the contribution of each and every entity in your problem. So this is simply a contribution technique. Cool. So now I will find the contribution of each index I. So the very first thing, I will fix I will fix A of I. So this is the first step. I will fix A of I. Now if I fix A of I, then what does it mean? It simply means I will fix A of I as maximum element. Maximum element. So what does it mean? So this is your one element, one index I. So the remaining indices, remaining k minus 1 indices must have their value of A is smaller than or equals to A of I. So for this thing, I will short this array. I will short this array. So short array A. And if I short this array A, let me write a generic solution here. So this array A was of size n. So I will short this array. So let's say we have A1, then A2. After shorting, then A3, A4, let's say A5 and A6. And then we have a corresponding element from this array B. So this is B1, then B2, then B3, then B4, B5, and B6. So here I have shorted the pair of A of I and B of I in ascending order of A of I. So let's say the value of k is 3. So if the value of k is 3, then what I know? I know if I select these three indices, if I select these three indices, then this A of 3 is having the maximum value, right? So this A of 3 is having the maximum value, and now you know the maximum value, and then you can just simply multiply A of 3, multiply A of 3, and the sum of these three elements of array B, the sum of these three elements of array B. Cool. This is my best answer. This is my best answer. This is my answer if I select A of 3 as the maximum element of array A among the picked indices. Cool. And then I need to shift this answer. I need to test for next value of A. So here this is simply equals to B1 plus B2 plus B3. Sum of these three elements. We do not have any possibility. Then I need to check for A4. So what if this A4 is the maximum element of your selected indices among array A? So in this case, now we are free. Now we are free to choose any index. Now we are free to choose any k minus 1 indices from the left part, because I know whatever the index I will choose, A of 4 will always be greater than the value of A at that index. So no matter which index you will choose. And now my A of 4 is fixed. Now my if of 4 is fixed, and this B of 4. Because if you have selected index 4, then this B of 4 will also be included. And now you are left with a choice to select a k minus 1 indices. So which k minus 1 indices I will select? I will select a k minus 1 indices such that the sum of B is minimum. Such that the sum of B is minimum. And how I can find this minimum? Let's say B1 and B3 is k minus 1 is smallest element from the left. So plus B1 and plus B3. So in this way, you can fix every index I, and A of I is the maximum element from 0 to from index 1 to I. And then you just only need to pick k minus 1, you only need to pick k minus 1 minimum element. Minimum element from a subarray, from a subarray 1 to I minus 1. Here I have considered the one base indexing. And this is a very standard problem, and it can be easily solved with the help of a priority queue, with the help of a max heap. Every time when the size of the max heap is equals to k, remove the maximum element. So is the approach is clear to you? Just write a quick +1 if the approach is clear to everyone. So just write a +1 so that I can move to the next problem. So I guess the Python support has there, also there. So from here you can just simply this select this Python 3. Cool. So here is the implementation. So first I have created an vector of item where each element is a pair. So the first element will store a of I, and the second element will store b of I. Then here I have taken the size of array a, and b has also the same size. Then I iterate over all the indices from 0 to n minus 1, and just simply push a of I comma b of I, because I need to sort this item vector which is of pair in ascending order of a of I. So that's why I put this a of I at the front, and then this b of I, so that by default it will sort according to a of I values. Then sort this item, and this is my total, and this total will store the minimum sum from the subarray b of 1 to I. Then here I'm having this my this max heap, and this is the first window. You can consider this as the window. That is this is my first k elements. For this, the value of total is fixed because you only have k indices. So yeah, that's why I will iterate over the first window, and just simply add the value of b of I in variable total, and also I'm adding this in the priority queue. Then this is my result. Items of k minus 1, that is maximum value of a of I multiplied by total. Cool. And then I iterate over the remaining indices, which starts from k. So the very first thing I need to remove the largest element. I need to remove the largest element from the max heap, because this was your first window. This was your first window, right? And then I will iterate over the remaining indices. Remaining indices, these indices, right? So the very first thing, I'm going to include this index, right? I'm going to select this index. So you must have to deselect some index from the previous window, right? Because we have to select exactly k indices. So in this case, which index I will remove? The index which has the maximum value of b, which is in this case this p of 2. So from the previous window, I will remove this index. I will remove this index, and then I will select these three indices. This b of I is fixed. This a of this index 4 is fixed. Then I will select this one and this one, because these has the minimum sum from array b. So that's why I'm removing the topmost element of this max heap and subtracting my total by that maximum element, and then adding the current value of b of I, and also pushing this b of I in a max heap. And then what will be my result? So this is simply equals to a of I multiplied by this total, and a of I has stored in item of I dot first. And make sure to convert it into a long, otherwise you might get an overflow issue. And finally I will return my result. So this is the complete solution. So shall we move to the next problem, or is there any confusion? What will be the time complexity? So in this case, the time complexity is order of n log of n base 2, because we are sorting the items array which is of pairs, and plus n multiplied by log of n log of k base 2, because at any point of time the max heap does not have more than k elements. So that's why it is log of k base 2, not log of n base 2. So now let's just quickly discuss the last problem of the contest, which was really very amazing if you know binary lifting at all. So the problem was named as a Santa's Christmas journey, and Santa is preparing for a Christmas and plans to give presents to n children, each in a separate house, and the house are connected by n minus 1 snowy trails represented by array trails. So this is a 2D array where each element is u comma v. So this is a 2D array of dimension n minus 1 cross 2, and each element, each edge, this is simply edge u comma v, indicates that there is a direct trail between house u and house v. So the Santa's journey plan is given by an 2D array. Journey plan consists of m roots, and each root is represented by two integers, start house and end house, meaning Santa will travel between these houses, passing through all the houses along the way and distribute the present. And your task is to determine how many presents each child will receive after all the journeys in the plan. And the village is connected, forming a acyclic graph with exactly n minus 1 trails. So this is simply means a acyclic graph where the number of nodes is n and the number of edges are n minus 1. So this is nothing but a tree. So you have this tree. Now let me just quickly explain you some simple test case. And if you haven't know the binary lifting technique, then you may skip this problem at this point of time. But yeah, the prerequisite is binary lifting to find the LCA. So the value of n is 5 and the value of m is 3. Then these are the n minus 1 edges of the tree. So there is an edge from 1 to 2, Then there is an edge from 1 to 3. Then edge from 3 to 4. And edge from 3 to 5. Cool. So here is the journey plan of a Santa. So for the first journey, the Santa will visit all the houses from house with the number 1 to house with the number 3 and distribute 1 candy. So initially all the houses has a 0 candy, and then Santa will visit all the houses from house with the number 1 to house with the number 3 and distribute 1 candy. So now this has changed to 1 and 1, 0 plus 1. Then the second journey, that is all the houses from house number 2, in the path from house number 2 to house number 5. This simply means these houses 2, 1, 3, 5. Cool. So how these values will change? Just simply add 1. So this is 1, and this will become 2, this will become 2, and this will become 1. So 2, 2, and this is 1. Cool. Now the final journey, which is from 1 to 4, the path from 1 to 4. So here I have to add 1. Then again here I have to add 1. So 1 to 4, this path. So this become 3, and this become 3, and this one will become 1. And after all the m journeys, you need to report the number of candies received by each house from 1 to n. Here one base indexing has been considered. So the value of node 1, which is 3, then value of node 2, 1, then the value of node 3, again 3, then 4 and 5, we have 1 and 1. So I hope the problem statement is clear to you all. So how we can solve this problem? And we need to perform every query, or you can say every journey, efficiently, either in a constant time or some logarithmic time. Quadratic time complexity won't be possible here, because the value of n and m both can be up to 10 power 5. So we need to do something better. And that something better is binary lifting, LCA using binary lifting. Now let's just quickly discuss a very brief overview what is LCA using binary lifting. So if you don't know what is LCA, so LCA is the lowest common ancestor of node u comma v. So what is the LCA of 2 comma 3? So 2 comma 3, the LCA is 1. So LCA is simply the last node which is common for both the node u and v in the path from root node to u, and in the path from root node to v. So in this path, one is the root node, and here this one itself is the last common node in these two paths. Now what is the LCA of 4 comma 5? So the LCA of 4 comma 5, this is simply equals to 3, the last common node, and LCA of let's say 3 comma 4, LCA of 3 comma 4. So in this case the LCA of 3 comma 4 is 3 itself, because this is the path from root to 4, root to node 4, and this is the path from root to node u. So in this case the last common node is 3 itself, because 3 is in the path from 1 to 4. So that's why here in this case the LCA is So at this point of time, let's assume I know the LCA. So how I will find the LCA, I will discuss this thing very soon. But let's assume at this point of time I know the LCA. So if I know the LCA, then how I can solve this problem? So the very first journey, which is from 1 to 3. So here 1, 2, 3. So basically this path. So LCA of 1 comma 3. So the LCA of 1 comma 3 is 1 itself. So what you can do, you can just simply add 1 here. That is, initially all the node has value 0. All the node has value 0. So create one array. Let's call this array as a prefix sum, because after executing all the queries, you need to take a prefix sum. So this is LCA. So what I will do, I will just simply add 1 here. I will add 1 here, and then what next? I will add 1 here, and also I will add 1 here. Then what does it mean? So after this, whenever if you take a prefix sum, what is I mean by the prefix sum? Prefix sum simply means for every subtree, add all the values for every node, add all the values of its subtree nodes. For example, here in this case, the subtree of node 3, the subtree of node 3. I will not add 1 here. A very obvious thing. I will not add 1 here. So here in this case, what will be my answer? So here in this case, just simply add all the values of the subtree node in the current value of a node. So here all the subtree nodes has value 0, then 0 plus 1, it is simply equals to 1. Because there might be the case when there has some operation which is performed here, which is performed between these two nodes, 2 and 4. So if there is some operation which is performed here, 2 and 4, so this simply means I need to add 1 here and I need to add 1 here, right? And so that whenever I take the sum of all the values of subtree, then this simply the value of node 3 is simply equals to 1, its own value, plus 1, and plus 0, the value of 4, and plus 0, which is equals to 2. And this is true as well. This is true. Here here when you consider this query, that is 2 to 4, then you also need to add 1. You also need to add 1 in node 3, because this node 3 is in the path from 2 to 4. So the path from 2 to 4 has a 4 node 2, then node 0, then node 3, the node 3, and then node 4. So I hope this thing is clear to you all. Cool. And for these type of query, I will subtract 1 from here. I will just simply add 1, and then I will subtract 1 from here. So that is simply equals to 0. This is for the first. This is for this query. So if I somehow get the LCA, then I can just simply then I will just simply subtract 1 from the LCA and add 1 and 1 add value 1 at node u and v. Add value 1 at node u and node v, because so that after performing all the m queries, when you take the prefix sum simply means the sum of all the node value in the subtree of every node, and then eventually this plus 1 and minus 1 will get cancelled out, and this turn out to be 0 for the LCA case, and you will get the sum of node values in the subtree, because for all the path, this node also has included in the path. Now let's just quickly discuss how we can find this LCA. So how we can find this LCA? So LCA using binary lifting. This is a kind of a quick revision for this for LCA using binary lifting. I'm not going to explain how it is working for because for this you need to know about Euler-Tour and sparse table. So binary lifting. So here there is a base case. So let me draw some tree here. So let's say this is a tree we have. I'm not going to draw it. I'm going to draw very simple tree just for an educational purpose. So let's say this is the tree, and this is, let's say this is node U, and this is node B. So I need to find its LCA. What is its LCA? This node is a LCA, right? So how I can find this thing? So uh, we all know anything, any number can be represented as a power of 2. Any number can be represented as a power of 2. So for this, let's just declare a DP array, 2D array, DP of I, comma j. And what DP of I, comma j will store? DP of I, comma j will simply store, please try to pay more attention, 2 power jth parent, 2 power jth parent of node I, 2 power jth parent of node I. So here we have a base case. But before finding the base case, let's just quickly discuss what is the maximum value of I. So we have I is simply a node number, right? So this is n, or actually it is n plus 1 if you consider one base indexing. But let's just say n, or let me write n plus 1. And what are the maximum possible value for j? So it is 20. This is 20 only. Up to 20 is enough because 2 power 20, 2 power 20 is greater than 10 power 5. 2 power 20 is greater than 10 power 5. So you don't need to consider the values beyond 20 for j because those parent does not exist. For any node, 2 power 21th parent does not exist. Cool. And yeah, these are the dimensions of your DP table. Then base case DP of I, comma 0. This is simply equals to P. It's a immediate parent. For example, for example, for this, the 2 power 0th parent. 2 power 0, that is the first parent. So the first parent is immediate parent. This is the first parent of node U. This is the first parent of node V. And now how I will find for the remaining, how I will find for the remaining values of J. So then just simply iterate. Then just simply iterate from J is equals to 1. J is equals to 1 and up to 19 or less than 20. Let's just consider 19. Up to 19. And then dp of I comma j, that is 2 power jth parent of node I, is simply equals to dp of I comma j minus 1 and comma j minus 1. That is j minus 1th parent of j minus 1th parent of j minus 1th parent of node I. Yeah, this is the idea. Do not get confused. You don't have to confuse here. I will explain you with an example. So how I will find the value of dp of I comma 1, I comma 1. So let me just also number these nodes. So let's say this is 1, this is node 2, this is node 3, then this is node 4, then 5, 6, and let's call this as 7. So here we all know this is a node 4. We all know dp of 4, dp of 4 and 0, dp of 4 and 0, that is 2 power 0, which is first parent of node 4. So the first parent of node 4 is 3. Very straightforward. Then what is the value of dp of 4 comma 1? This was 0, sorry. So dp of 4 comma 1. So this simply means 2 power 1th parent. That is a second parent. Second parent of node 3, of node 4. Second parent of node 4. So how I can find the second parent of node 4? So the second parent of node 4 is simply equals to the first parent of node 3. Very straightforward. If you want to take the if you want to calculate the second parent of node 4, which is 2, so I can also say this is nothing but the first parent of node 3. So this is nothing but the first parent of node 3. Take a jump from here and then take a jump from here from 3 to 1. The first parent of node 3. So this can be written as dp of 4. So this can be written as dp of 4, and then 1 minus 1 minus 1, which is 0, and then dp of 1 minus 1, which is 0, which was 0, right? So this is nothing but 3. This is equals to 3. So this simply means the first parent of node 3. Similarly, you can break for other values of j. For example, j is equals to, let's say j is equals to, let's say j is equals to 2. So how I can write this thing? That is how I can write this thing, 2 power 2, which is simply equals to 4. So this can also be written in this way. That is 2 power 1 plus 2 power 1. That is, if you need to calculate the, let's say this is your current node u, this is your current node u, and you need to calculate, its 2 power jth parent. It's a 2 power jth parent. Let's say it is at here. So this can be easily broken down into 2 power j minus 1, 2 power j minus 1, 2 power j minus 1, and then 2 power j minus 1th parent of this node. So 2 power j minus 1. So eventually I can say 2 power jth parent of node u. So I have just divided it into halves, and we already know these values. We already know all the values for the parent node. We already know all the values for all the possible j for the parent node 3, and we also have this value. We also have this value dp of I and j minus 1, because we are iterating from the smaller values of I, to the bigger values of I. That's why we have this. Cool. And in this way you can fill this dp table. Now after filling this dp table, how I will find the lca, how I will find this lca? So this is again a very simple. Let's say this is node u, this is node 1, then node 2, then let's say node 3, then node 4, let's say we have node 5, and then node 7, and let's say node 8. And also let me write here, let's say node 9. So let's say I need to find the lca of a node 9 comma 7, node 9 comma 7. So how I will find this lca? So node u, that is node u is this one, and node v is your this node. So the very first thing, first I need to move this node v to the same level as node u, and once they are reaches to the same level, then I can just simply take the same number of jump to reach to the lca, to reach to the common ground. So I hope this thing is clear to you. So first I will find the difference in their heights, and then I will move this node u to the same level as node v to the same level as node u, and then I will take the common jump for both the node until I reach to the same node. So here in this case, let's say this is height 0. This is a height 0. Here I am writing the height of the node height. So this is height 0. Then this is height 1. Then this is height 2, and this is height 3. So the very first thing what I know, their height differences. So h of u, and here I am assuming that this node v is having a greater or equal height than node u without losing generality. So I am assuming, just for a simplicity, I am assuming h of v is greater than or equals to h of u. And if h of u is greater, then just simply swap u and v. You will not lose a generality of this entire problem. Now, what will be the difference? So the difference is simply equals to h of v minus h of u. So here in this case, this is a 3 minus 2. This is the 3 minus 2, which is equals to 1. So what I can do, I can just simply reduce this difference. I can just simply reduce this difference to 0. Reduce this difference to 0. And we all know I can represent any integer in a powers of 2. So this 1 is nothing but the 2 power 0. So from here, just simply move to its 2 power 0th parent, which is this node, this node 5. I have now moved to this 2 power 0th parent, which is this simply means I am now at node 5. And once you reach to the same level, then just simply take a common jump. Take a common jump. And let's say we have some difference other than this 1. Let's say we have a difference as a 13. We have a difference as a 13. So we all know the binary representation of 13. This is 1 1 0 1. 8 plus 4, 12 plus 1. Cool. So what does it mean? It just simply means move to 2 power 3th parent of node v, and thereafter we are at some other node, and then move to 2 power 2th parent of that node. Then we are at some other node. So initially we are at v, and let's call this as a v dash, because now I have shifted to 2 power 3th parent, and then move to its 2 power 2th parent. So this is called as, let's call this as b dash, and then move to its first parent, that is 2 power 0, right? Yeah, 2 power 0. So move to its first parent. Move to its first parent. So let's call this as v triple dash. Now you are at some node, and that node is at the same level as node u. And now you can take the common jump. And how much time it will take? This is nothing but the log of difference by 2. Not by 2, but the base 2. So I guess this is the complete explanation. Now let me just show you the implementation. If there is something which is not clear to you, then I would highly suggest that go and learn the binary lifting, and then come and try to solve this problem. So yeah, this is the method that you need to complete. Calculate present count. So first I have created this height vector as per the discussion, and I have initialized every height with a -1. You can also initialize with 0. That's totally up to you. Then here is my DP table, which I have named as ancestor matrix, and of size n plus 1 because of one base indexing, and then this 20, because we all know that 2 power 20 is greater than 10 power 5, and 10 power 9 is 10 power 19 is also greater than 10 power 5. So 10 power 20, 2 power 20 is not possible. So that's why up to 19 is enough. Then initialize all the values with 0, and then this is my adjacency list. Then a prefix sum vector, and then the visit count. So visit count is nothing but how many time I have visited each node. This is my answer vector. Then here I have created a graph, and then I will call this function calculate height and ancestor for every node. Then here I am passing the basic required parameters, adjacency list, then height vector, and this DP vector, or you can say ancestor matrix. Then initially my height is 0, right? And initially I am at node 1. Here I hanged the tree with a reference to node 1. You can use any node, it's totally up to you. So I have fixed this one as a root node. It is not given in the problem statement. You can consider any node, and then assuming its parent, imaginary parent 0, because 0 is not possible. All the nodes are numbered from 1 to n, and then yeah, this is the function. So this is my base case, right? This one is my base case, right? 2 power 0th parent, that is first parent, is the immediate parent of the node. And then I'm filling all the other DP values. So this is nothing but DP of I. Let me just quickly comment out this thing. So this is nothing but DP of I j, and it is simply equals to DP of I, DP of I j minus 1, j minus 1th parents, and then j minus j 2 power j minus 1th parent of that node. This is simply, here I have named this j as shift, and this was my base case, and this is the height of the current node. Then I iterate over all its neighbor, and a very trivial DFS function. And if the neighbor not equals to parent, then make a call and increase the height, increment the height by 1, and everything will remain as it is. Cool. And in this way, I will fill this a DP table. And after this, once you are done with this, once you have filled this DP table, then I iterate over all the journeys, all the queries. So this is my start house, and this is my end house. So first I am finding the common ancestor, lowest common ancestor. So for this, I am having this function, and it takes 4 parameters: the start house, end house, and heights vector, and this DP vector. So lowest common ancestor, which one? Yeah, this one. So here I am assuming node A has height greater than node V, and if node V has height greater than node A, then I will just simply swap these two nodes. Then first I will bring both the nodes to the same height. So for this is the current difference. I need to reduce this difference to 0. That is height of A minus height of B. I need to bring both the nodes to the same height, and then I will move this together. So yeah, this is a function to bring both the nodes to the same height. So here shift is equals to 0, and then then here I'm just simply iterating over the binary representation of this difference, and if the bit is set, then I will take the jump, and here you don't have to write this case, and then I'm just simply removing this bit and also incrementing the shift. This is a very simple way of iterating over all the set bits. So I'm not going to explain you this function because we are discussing the binary lifting. So I'm expecting you guys are all already know about these things. Anyways, so once the difference has reduced to 0, then there might be the case when the node A and node B both are same. So this simply means the LCA is among node A or node B initially. So in that case, I will just simply return node A. Let me just give you an example. So let's say you need to find the LCA of node 3 and node 7. So here the difference is difference of 2 we have. So for difference of 2, if you reduce this difference to 2, if this is node V, then you will move to here, and now you are at the same level, right? And or I can say at the node 3 itself. So this 3 will be your LCA. So that's why I'm returning this node A. Otherwise, I iterate over all the values of J or the values of shift from 19 to 0, and if their parents are not same, if their parents are if their parents are not same, 2 power jth parent are not same, so this simply means we can take this jump. So just simply take a jump, and after this, whenever you reach to whenever you do you will reach to these node, whenever you reach to these node, let's say this is a u dash and this is v dash. So in this case, its immediate parent, that is 2 power 0, 2 power 0th parent, 2 power 0th parent, and a 2 power 0th parent, both are the same. So this simply means that this one will be my LCA. This one will be my LCA. So I'm just simply returning this one as a LCA. And once I get this LCA, then what I will do, I will just simply increment the value of start house by 1, increment the value of end house by 1, and then I will simply subtract -1 from here. And also I will subtract -1 from its ancestor, because I don't want to forward these values. I don't want to propagate these values in an upward tree. So that's why here I have to cancel out. So these two I have added, and then I'm subtracting -1 from here, and then I'm also subtracting -1 from the immediate parent of the LCA. So in this way, after this, you can just simply add the values of all the subtree nodes for every node. So here I'm just iterating from 1, and this time I have taken this imaginary parent as -1. You can also take 0. I don't know why I have written this -1, and then these are the required parameters. So yeah, this function. So calculate prefix sum. So this is the total visit, which is equals to its value in the prefix array, and then I iterate over all the neighbors, and for every neighbor count count the values in their subtree, and then for the current node, it is simply equals to the total visit for this node. All the subtree node values sum. Very straightforward. And then I have subtracted -1 from here to convert it into a zero-based indexing. And then finally, I am returning the total visit for the current node to calculate the total visit for the parent node. So yeah, this was the complete solution. How much time it will take? So this is n log of n base 2, and plus m log of n base 2. So let me just quickly discuss how much time it will take. So this is log of n base 2, because you are building this ancestor matrix. So that will simply take n log of n base 2, and plus m number of journeys we have, and for every journey we are finding the LCA. So that will take log of n base 2. So yeah, this was the time complexity. So these are the explanation for all the three problems of the contest. I hope you have learned something new. So in case if you are having any doubt, then please go ahead. Otherwise, we can wrap this session. So in case if you have learned something new, then please hit the like button, and also make sure to write your comments write your comments so that I can improve these sessions in the future. So I guess no doubt so far. So thank you so much everyone for joining this session, and have a good day.